So I am pleased to introduce Stephen Gustafson from University of British Columbia. Stephen will talk about chiral magnetic skyrmions of 2D Landau-Lifshitz equations.
Thank you very much, and thank you to the organizers for the opportunity to speak here. And thank you all for staying late to accommodate my time zone. That's quite appreciated. So my plan here is to give a little bit of a survey style talk about aspects of the Landau-Lifshitz equation, but mainly the interest is in topological solitons, and especially these ones that are called chiral skyrmions, which I'll get to in this second half of the talk. But I'll start with some generalities about the Landau-Lifshitz equation. Okay, so there is this old theory, this phenomenological continuum theory describing magnets called micromagnetics, going back to Landau-Lifshitz, where the idea is to somehow capture the domain structure in magnets, and as well as the domain wall structure. So let's see here. I can write, yeah, okay. As well as the domain wall structure and how domains transition one into the other. And the way this is done is through this magnetization vector. So the main dynamical variable here is this magnetization vector, which is a vector field on, so everything here in this talk will be on the plane. So this is a vector field on the plane, but with a unit length, pointwise unit length constraint. So we can think of this as an S2 valued map if we want, which is describing the direction in each of these domains in the magnet. Yeah, so there's statics, there's static questions, and then there's dynamic questions. So for the static configurations, what you're doing is you're looking at some energy functional associated to these magnetization configurations, and you're looking for critical points or even maybe minimizers of this energy functional. And so here's the energy that's relevant for today. So it's got various terms, including the crucial gradient squared or Dirichlet term, which captures the ferromagnetic aspect of the material. And then there's a term that I want to emphasize, especially in the second half of this talk, which is this one here, which is the so-called chiral interaction or Dzielaszewski-Moria interaction energy term, which is irrelevant for some materials, which are sometimes called chiral magnetic materials. So one of the themes will be the effect of this term in the energy. And then you might also have some kind of anisotropic energy like this one, which is a so-called easy axis anisotropy, which favors the M3 or the K axis. And you might also have the effect of an external magnetic field. So in this case, a constant field in the M3 or the K direction. Okay, so that's the energy functional. And if you want to find static configurations, you find critical points of the energy functional. And then there's a dynamics associated with the magnet, which is given by this Landau-Lifshitz equation written at the bottom of the slide here, which says that you have this energy functional. You can take the variational derivative of this energy functional and think of it as producing an effective magnetic field. And then the magnetization itself will precess in this effective magnetic field. So that's the dynamics. Okay, so I'm not really, I see there are things in the chat. I'm not really monitoring the chat. So if there are any questions, please just interrupt anytime. Okay, So to really understand this Landau-Lifshitz dynamics better, you should look at the structure that it has. So it has a nice Hamiltonian structure and a nice, if you like, geometric structure. In particular, you can write it in this general Hamiltonian form, provided you make sense of all those quantities on the right-hand side. So what you need to do is look a little bit at the geometry of the situation, which is very simple. So these are maps into the two-sphere. So the tangent plane at every point on the two-sphere is just the orthogonal complement of the vector itself. And then you can think of this operation of the cross product as a complex structure or a 90-degree rotation on this tangent space, which is the J that's appearing here in the equation. And then if you are careful to work geometrically, so for example, whenever you see a tangent, a vector field that takes its values in the tangent plane, a tangent vector field, you should differentiate it covariantly, meaning you should project the derivative back onto the tangent plane at each point. And if you then take the variational derivative or the gradient of the energy functional, keeping this geometry in mind and projecting back into the tangent space, then you can see that, for example, that the term generated by the Dirichlet energy gets a nonlinear correction. And that's where the nonlinearity in this problem is really coming from. And if that's all you have in the energy, if you only have the Dirichlet energy, then you can really think of this equation as a geometric generalization of the pure free Schrödinger equation for maps into the two-sphere. And this, in this guise, it's often referred to as the Schrödinger map equation. Okay, so we have some nice geometric and Hamiltonian structure. Just a couple of other things, related things to mention. There's a scaling for the Landau-Lifshitz equation in 2 dimensions, which is this one here, which is also the scaling which leaves invariant the Dirichlet energy, which makes this problem, if you like, an energy critical problem, in the sense that solutions can scale with no energy cost. And so this is a possible mechanism for collapse or singularity formation for the equation. And then secondly, there's a topological number that we should keep in mind. So for the rest of this talk, let's fix a boundary condition at infinity. So let's suppose that all my magnetization configurations at infinity are approaching this fixed ferromagnetic state, if you like, the fixed vector k in the M3 direction. Then we can think of these maps as maps between two spheres, to which we can associate the classical degree of the map, or in physics sometimes called the Skyrmion number. And this can be computed by the integral written here, and turns out to always be an integer. Okay, so this degree or Skyrmion number characterizes the topology of our maps. And I guess the main interest here would be in topologically non-trivial solutions. Okay, so before I move on to the solitons, I want to just say a little bit about the dynamics and some of the issues associated with the dynamical problem. Okay, so this slide is a little busy. There's a lot going on here. But the main point is just a question of how to make sense of what is a priori a little bit of a strange looking equation. In particular, your leading order term is looking highly nonlinear. And one way to make sense of it, to understand what it really looks like, is a standard method in in geometric equations, which is to not look at the map itself, but to look at derivatives of the map whose values lie in the tangent spaces, which are at least linear spaces. And so if you want to do that, you need to set up some orthonormal frame on the tangent space to the solution, or to the sphere at the solution at each point in space-time. So let's suppose we've done that. We set up this orthonormal frame. Then you can start taking various derivatives of the map and express them in this coordinate system. And the upshot, the conclusion, is that what the equation looks like at the level of its derivatives is like cubic Schrodinger equations, roughly speaking. So these size, remember, these are the derivatives of the map expressed in coordinates. D0 is a time derivative, and dl, these are space derivatives, but they are now covariant derivatives. And you can see that very, very roughly speaking, we have a cubic, something like a cubic nonlinear Schrodinger sitting here. And if we are to include also this chiral interaction term, we get a derivative, an additional derivative term in this system of Schrodinger equations. Of course, if this were a true cubic Schrodinger equation, then we would know a lot about it. We would have a lot of theory to access. But of course, it's more complicated than that, because of these derivatives, these covariant derivatives, are hiding the connection coefficients, these AJs, which themselves are dynamical variables. And so there's a bunch of extra derivative terms of both A and psi sitting inside those covariant derivatives. So that's bad. But on the other hand, something that's good is that you have some gauge freedom, because we can choose any orthonormal basis of the tangent space that we want. And so we can go from one to the other by just rotating the frame as we like. And this gives us the freedom to choose some extra conditions on the vector potential, or on these connection coefficients. So for example, if you want, you can choose a divergence-free vector potential, or the Coulomb gauge, which generates a nice elliptic equation for estimating the vector potential in terms of the fields. So that's one possible choice, but by no means the only possible choice, and not necessarily even the best choice. Okay, so the point of all this is just to say that this is something like a cubic Schrodinger equation, but technically much more difficult from an analytic point of view, because of these technical issues, how you control the vector potential, how you treat these derivative terms perturbatively. The well-posedness theory for these equations is really very, very much less than satisfactory. And there's an even bigger issue, in fact. If you're interested in topologically non-trivial solutions, which one should be, I guess, then the situation is perhaps even worse, because there is no way to construct an orthonormal frame. Now, for example, how this is often done in practice is, if you have a topologically trivial map, then you have a homotopy to a constant map, and you can use that homotopy to transfer some standard orthonormal frame back to your solution. In the topologically trivial, a non-trivial case, that this is not possible. And so the situation is even worse. So to make a very long story short, if you, in general, really the best well-posedness results, local well-posedness results for this equation are at the level of Sobolev regularity H3, which, if you like, is roughly 2 derivatives worse than what you would ideally like. So that the natural space is the energy space, which would be the Sobolev space H1. You can do better than this in the topologically trivial case by using this orthonormal frames approach, but still quite far from satisfactory. The one result where you really, general result where you really get down to the energy space regularity is this small energy result of Bejanaro, Ionescu, Kennigan, Tataru. But that's certainly very far from topologically non-trivial solutions. Okay, so there's a lot of open questions here. Can you lower the regularity for the well-posedness theory, and especially in the situation where you have topologically non-trivial solutions? Okay, so I think that's all I want to say about the well-posedness issues. And I want to move on to the main interest, which is topological soliton solutions. So to discuss this, I want to start with what is in some sense a trivial case, where you have only the exchange energy or the Dirichlet energy in your functional, and so your minimizers or critical points are just harmonic maps. So this is something that's very easy and classical to describe. So the first observation in this case is that you have a classical Bogomolny style lower bound for the energy in terms of the topological degree, or in terms of the Skyrmion number, just by completing the square in the energy function. And moreover, you can read off from this relation the condition that's required to minimize the energy within the given topological sector, which is really just the Cauchy-Riemann equations. So you can solve these explicitly. And once you've fixed the topology and you fix the boundary condition, then you get a certain family of explicit harmonic maps or explicit minimizers of this energy. To understand a little bit better this situation, it's useful to look at some symmetry classes. So there's a kind of symmetry which you can require called equivariance, where, so these R's, these are supposed to be rotations. So the idea is you do a rotation by an angle omega on the outside. You do a compensatory rotation by n times that many rotations on the outside, and that leaves the solution invariant. So that generates, assuming you choose your boundary conditions right, that generates a topologically non-trivial map where the winding number n is the same as the Skyrmion number. And then within this family of explicit harmonic maps, there's a remaining two-dimensional family which has this symmetry for any choice of n, and you can write it out explicitly. There it is. There's two parameters, so the parameters are a rotation parameter, and the important thing is the scaling parameter, because this energy has a scale invariance. Okay, so just to summarize this situation sort of vaguely physically, you have these solutions which are, let's say, topologically stable. So in the sense that they're topologically non-trivial, so they can't be completely destroyed by continuous deformations. They're even energetically stable in the sense that they are energy minimizers with fixed topology, so you can't destroy them without adding energy. But on the other hand, there's this remaining scale invariance, which still allows for the possibility of some kind of a collapse. So from let's say a physical or even a technological viewpoint, this is slightly less than satisfactory. But but you can look at this question of the stability of these solutions more precisely and mathematically. And so this is some older stuff on this slide here. So essentially you're asking about the dynamical stability of these harmonic map solutions as a solution of the corresponding Landau-Lifshitz equation, which in this case is the pure Schrodinger map equation. And you can look at this by winding number or by degree within the equivariant symmetry class. And it turns out that the higher degree ones are in fact stable, asymptotically stable, but this problem, if you like, of collapse can occur for the lowest degree maps. If you're interested in open questions, then here's one. Well, there's a gap in there somewhere, so somehow it's not clear what happens in between the n equals 1 blow up and the n greater than or equal to 3 asymptotic stability. And the other thing I'm not sure is particularly well known. What happens to this blow up phenomena in degree 1 if you include other terms in the equation, such as this chiral term that I mentioned, or indeed even dissipation, which is a physically natural thing to do. A couple of other relevant statements. So that's about topologically non-trivial or solutions near topologically non-trivial solitons. For topologically trivial solutions, what you might expect is that there's no mechanism for collapse, and so you would anticipate there's global existence for an equation like this Schrodinger map equation. For example, if the energy is restricted to be below the minimal energy for a topologically non-trivial solution, you would expect global existence, but this is still basically, as far as I know, an open question, modulo some small progress in a symmetric setting. Okay, so the main point there was just to indicate some, well, two things, to indicate some open problems, but also to point out that you have this instability due to formation of singularities if you take the pure harmonic case or the pure Schrodinger map case. Okay, so let's move on to the chiral situation. Okay, so now I'm going to restore these other terms in the energy functional. In addition to the exchange energy, we have the chiral interaction, an anisotropy, and an external field. And it emerged from the physics literature, I guess, in the 90s, that well, first of all, that there should be materials for which an interaction of this type is relevant, and secondly, that if so, then this could stabilize these Skyrmions or harmonic maps, whatever you want to call them, against the collapse and produce potentially stable topological soliton solutions, which would be, I suppose, desirable from a physical or technological point of view. And then sometime later, such objects were indeed observed experimentally. So there's some picture from some experimental physics paper. I guess experimental images on the right and cartoons on the left, and there's a parameter here which is an external magnetic field strength. When the external field is low, there's this, I guess, essentially one-dimensional structure, spiral phase. When the external field is very high, there's a pure ferromagnetic phase, but somewhere in between, you see these Skyrmion type topological solitons. either tightly packed in some kind of a lattice or a little bit more spread out and isolated. Okay, so what can be said mathematically about these solutions? Well, one thing you can do is you can look for symmetric solutions with this chiral interaction, and you can first of all observe that this equivariance transformation, where you rotate internally and externally by the same compensating angle, does in fact leave this chiral exchange interaction term invariant, even though it's not invariant separately by internal and external rotations. Which means you can, if you like, you can look at minimizers of this energy within the equivariant symmetry class. You can also restrict a little bit further. There's an additional reflection invariance. And the upshot of that is that if you want, you can restrict your search for minimizers to this even smaller symmetry class, sometimes called co-rotational, which if you have the right boundary conditions, this gives you a degree 1 map configuration, which is entirely described by a single profile function of the radial variable. Okay. So this is in fact what the physics literature, what was happening in the physics literature. So this is a picture from one of those papers, and so this here is the profile function, which is connecting. It's an angle. It's connecting pi at the origin to 0 at infinity to generate these topologically non-trivial Skyrmion type solutions. Okay, so what you want to do is use this as an ansatz and minimize the energy in this class. Okay, so if you do that, you end up with an energy functional like this. In terms of this profile function u, and your problem, you impose appropriate boundary conditions and look in an appropriate function space and consider the corresponding minimizer. Okay, so there are some mathematical results about this minimizer. First of all, the result of Lee and Melcher in a certain setting, and in particular in a certain parameter regime where this coefficient in front of the chiral term is small. So in this asymptotic regime, they were able to show that this solution has many favorable properties, that the profile is monotone, the solution is unique, and that indeed this generates a stable topological soliton solution, and stable in the sense of stable against perturbations which are even outside of the equivariant class. And then I'd just like to describe briefly some work I did with a graduate student, which is along the same lines, but gives some more, let's say, more precise information about this, the profile of this Skyrmion solution. In particular, the idea is to relate in this same asymptotic parameter regime, is to relate the profile of the Skyrmion to the profile of the harmonic map, suitably rescaled. So there's a length scale in there. And part of the difficulty here is identifying exactly the length scale. In terms of the parameter, there's this logarithmic correction. And giving some precise estimates on the error term after removing this bubble, if you like. So that's one statement, and then related to that, once we have this asymptotic information, it's possible to say something fairly precise about the stability in particular about the size of the spectral gap, or the energy well, if you like, giving the stability of this Skyrmion solution. Okay, so the main point here is to give some kind of quantitative description of the Skyrmion profile in this parameter regime. I should point out also recent work of Bernard Mantel, Muratov, and Simon, which is doing something similar by very different methods outside of the equivariant symmetry class, but with somewhat less sharp estimates. Okay, and then this one advantage of this approach is that it gives you a mechanism for proving stability without necessarily knowing that you have a monotone profile, which is not clear for all the parameters. Okay, so let me say just a little bit about where this comes from. Oh, first let me give you some open problems. Okay, so the first open problem, as far as I know, is, okay, so we have this equivariant minimizer. There's also a global non-symmetry constrained minimizer, and it's not clear if those two agree. So there's an open question, a pure calculus of variations question, I guess, about the symmetry of the global minimizer. Secondly, I guess the only thing we really know is in the regime where this coefficient is small. And mathematically, we don't know much outside of that. And then thirdly, I guess an important open problem would be the dynamics. So these solutions they're stable in the energetic, or if you like, the spectral sense, but then there's this question of whether you can prove they're honestly dynamically stable as solutions of the Landau-Lifshitz equation. Okay. So now just a few words about where this relation between the Skyrmion profile and the harmonic map profile comes from. And you can see it right away from rescaling the energy functional. So the exchange term in the energy is scale invariant, but the other terms break the scaling invariance. So you can play around with their parameters but their coefficients by scaling. And so you can see that in principle, if you can send k to 0 and beta to 0 at the same time, and scaling to 0 at the same time, then what's left is the isotopic problem, the harmonic map problem. And so the question is how to relate the minimizers of the one problem to the minimizers of the other problem, keeping in mind that the isotropic problem has this scale invariant, so you don't just have one minimizer, but in fact a one parameter family. Okay, and so rephrased this way in terms of the scaling, the problem is to figure out what should be the relationship between these two parameters, k and the scaling parameter beta, in order to ensure that this limit really is the harmonic map profile q, and to get some more or less sharp estimates on the rate of convergence as the parameters go to 0. Okay. So what's behind this? Okay, so this slide, this is the part where you verify that there's at least some choice of scaling beta for which the minimizers of this chiral problem converge to some harmonic map profile. This is a more or less standard, I guess, sort of baby concentration compactness argument. So I won't say anything about that. So what's really going on here, you can see by looking at the Euler-Lagrange equation. Okay. So once you've established that your true solution, let's see, is harmonic map profile plus a remainder term where the remainder term is going to 0 in some appropriate norm, then you can look at the Euler-Lagrange equation for the remainder term. And in particular, look at the linearized operator that appears there, and observe that its unperturbed version has a resonance eigenfunction. So in other words, an eigenfunction which it's explicit, but it does not lie in L2. It has slow decay. Decay is like 1 over R. And this is exactly coming from the scale invariance of the problem. And in fact, it's this resonance eigenfunction which is dictating the length scale. And the way you can see this is by doing some kind of a resolvent expansion in this parameter beta, and observing that, of course, there's a singular term in the resolvent expansion corresponding to this resonance eigenfunction at 0 energy. If it were an honest isolated eigenvalue, you'd have a 1 over beta squared, but it's corrected by this log factor because it's a mere resonance eigenvalue. Okay, but of course you want this error term to be small as possible. So the natural thing to do is to try to kill off the singular term that appears in the resolvent expansion, which gives you this orthogonality condition. And if you analyze carefully this orthogonality condition, that's what determines the relation between K and beta, which is what gives you the length scale of the harmonic map profile that's describing the chiral skyrmion. Okay, so the whole thing is somehow driven by this threshold, energy 0 threshold resonance. Okay, and then there's some business to go through to get higher order estimates, which is not so important here, so I'm not going to go into it. Just that the key is somehow to use this nice explicit factorized form of the linearized operator. Okay, but let's avoid the details there. So that's to show that the chiral skyrmion profile can be well approximated by a rescaled harmonic map profile. And then the next step is to use this to get stability information. Stability information means that we want to look at the linearized operator, or second variation of the energy about the Skyrmion solution. You can, because of the symmetry, the equivariant symmetry, you can make a Fourier decomposition in the angular variable on the plane, and so you can reduce this study of the second variation operator to a series of matrix valued operators acting on radial functions. And really what this is it's a perturbation of an explicit linearized operator, which is this one here. And this is exactly the same operator we saw before. It's the one with the 0 energy resonance eigenfunction. And so the question here is how to do perturbation, spectral perturbation from a threshold resonance, in particular when the perturbation, the potential, if you like, of perturbation has very slow spatial decay. So that's kind of the technical issue here. And let's not worry too much about the details here, but maybe look at the picture. So I guess the main point here is in the picture. So for your unperturbed problem, you have essential spectrum. going down to 0, and you have this resonance eigenfunction sitting at 0 energy. When you make the perturbation, you introduce a gap between, okay, so these are shifted operators. So this is really, for the shifted operator, that's really the 0 energy. Okay, so when you make the perturbation, you introduce this gap between the 0 and the essential spectrum, and you want to know how the eigenvalue can bifurcate from this resonance eigenfunction. And so what you want to make sure doesn't happen is that it can go all the way here, and that would produce an unstable eigenvalue. So the point is to show that because it's coming out of this resonance, you have, it doesn't move by beta squared, but it's corrected by this log factor, which keeps it on the stable side. Okay, so this, it becomes a little bit technical, but that's the main point. Essentially, you can do this again by resolvent expansion. So if you have some would-be eigenfunction, you can look at the equation, the eigen equation, expand the linearized operator in the same way as before, and understand that, again, you have the singular term, so there's an inner product which is necessarily small. And so you can determine the size of this potential eigenvalue by looking at this inner product. Okay, but the main thing is that it's a perturbation, spectral perturbation theory from a 0 energy resonance. Oops, okay, what's this? Okay, so this is just dealing with, so what I described before was really dealing with the perturbations within the same symmetry class, and then there's some work to do to show that you still have stability outside of the symmetry class. Okay, but I think maybe that's enough about the isolated topological solitons. So the last thing, just very briefly, that I want to discuss is lattices. So here, again, this is the same physical picture from earlier on in the talk. So it's clear that in practice, these in experiments, these skyrmions don't appear as isolated objects, but in fact, in some kind of a lattice. And there's maybe some nice mathematical questions here, but at this point, we don't know very much. So I'd just like to describe briefly this recent work of Lee and Melcher on this problem. So what they're doing is they are looking at periodic configurations, so configurations, magnetization configurations, which are periodic with respect to some lattice, and then doing some bifurcation analysis, essentially linear bifurcation analysis. And really from the 0 state here. So this is not the same as the maps into the sphere we were talking about before. So here the unit length constraint has been dropped, and instead you're looking at some, if you like, Ginzburg-Landau type energy functional, but again with this chiral term involved. And considering what are the possible bifurcations from this trivial 0 state with different lattice periodicity. And what they find is several possible patterns, at least at the linear level. So one of the patterns is this helical pattern, which is really, I guess it's what in this picture is called the spiral state. Is essentially a one-dimensional configuration. Another pattern that's observed is this vortex, anti-vortex type pattern. And then the thing that maybe is the most interesting is the skyrmionic pattern, which is something that at least at the linear level is looking like a skyrmion lattice. Interestingly, they only find this for one possible lattice geometry, which is the hexagonal lattice, and not for the other shaped lattices. And also interestingly, they find it's unstable, at least in this regime, at least as a bifurcation from the zero state. On the other hand, there's some numerics, they do some numerics for the model with the honest to goodness constraint, where you're really looking at maps into the sphere. And in certain parameter regimes, they do actually observe skyrmion lattices, like we see in the experimental picture. And the fact that they're observed numerically suggests that indeed there are such stable configurations for the full unit length constraint model. As far as I know, there's no analysis here, so this could be a nice, interesting direction of investigation for the future. And I guess I went faster than I thought. I'm actually done, so I will stop there and thank you for your attention.
Thank you very much, Stephen. So, more questions?
Yes, I have a question, Stephen. This is Etienne. I wondered whether you have like degree 2 axis like you have for harmonic.
In the chiral case, you mean?
Yeah, in the chiral case.
It doesn't. It's not preserved. So that chiral term in the energy is not invariant under a higher degree equivariant transformation. That essentially forces you into degree 1.
All right.
Okay, so maybe Radu.
Yeah, hi Stephen. This is Radu.
Hi.
So it's a bit like Etienne question. So it was about Skyrmion with degree -1, because yeah, as you said, the Jaroszynski-Moria, I mean, okay, if you want to keep the boundary, so like this E3 state at infinity, then well, there is no symmetry to go to -1. So, well, I know a bit the paper of Mel here. So there, where he tried to do the usual method, like minimizing within a prescribed Skyrmion number, it didn't work for if that number is different than 1. So like Etienne asked, so okay, is there some other? So is there other method? It's true. I'm not aware about the late works, but so I mean, trying to do differently. I mean, like for the harmonic map problem, you can just run the harmonic map flow, and so that's quite different than just doing this concentration compactness method. So
right,
is this something done?
So I guess what you could do is, so if I think about this, so once you've assumed your equivariant symmetry, you have this reduced energy functional, and it has this coefficient K in front, and I've already chosen, let's say, a profile which connects pi to 0. I suppose going from 1 to -1 would be essentially flipping the sign of the coefficient on the chiral term.
Right, but then you have to change
and asking if I have a minimizer.
Right, but so I think
the answer to that is I don't know. I mean,
So if
I don't know if there is a minimizer.
So I mean, within this radial symmetry you look at, I think the only ones are this degree 1. So there I think it was quite clear. I mean, but yeah, you should. I think they should appear with a different symmetry, if any.
But
So,
you're
okay.
perhaps proposing choosing a different degree and just running some gradient flow or something to see what happens. Which sounds totally reasonable to me. I haven't done anything like this, and I haven't seen anything like this. But why not? Yeah, I mean, it sounds totally reasonable.
Okay. And sorry, just one quick question. So in this lattice that they observed there, all the Skyrmions are degree 1, or it's okay, because you said vortex anti-vortex. I thought it's like Skyrmion 1 and -1. So then what is -1? So okay, but if you say it's 1, okay, thanks.
Thank you, Radu. So maybe I have also a question, Stephen. So regarding the open problem you mentioned at the end, so are there periodic solutions with this unit constraint? So are such solutions constructed or not yet?
No, I don't think so. I mean, you could imagine various ways of trying to do this. For example, gluing together some relatively isolated Skyrmions, so you have some approximate solution, and somehow improving your approximate solution. If you want to produce solutions with that particular structure, but as far as I know, that hasn't been done. So yeah, I don't really know any good results along these lines.
Okay, thank you. So just now I noticed in the chat box, Fahad Daibis has a comment on technology applications. I don't know if you have something to say about it. So he is saying magnetic Skyrmions can be used to store information in future memory and logic devices. I don't know, maybe if you...
I have no special insights about that. Just I do think that's why there's so much interest in physics and engineering directions in these things.
I just wanted to come...
of course, I'm mainly interested in the mathematics. Yeah. Sorry, Etienne.
If I can come back to Radu's question, just to check that I understand things correctly. So if you minimize in the energy in the degree -1 case, so it's not known whether there's a minimizer.
As far as I know, I mean, Melcher looked into this, and they found, I guess, their convention is probably different than mine. So they called it n = -1, but it's what I'm calling n = 1 is where they proved the existence of a minimizer. And I don't know what happens otherwise.
So Etienne, if I remember well, what they proved is that when you minimize your energy, so no matter what the degree is, the minimizer will have this degree -1, what Stephen called degree 1. So and for all the others, when let's say you are looking for local minimizers within another fixed Skyrmion number, they don't find it. Of course, besides the trivial one where you just take the constant state. But so that's why.
You mean by, what do you mean by they don't find it? I mean, they prove that it's not attained, or
no, the method, so the concentration compactness doesn't work. So you cannot conclude it, but of course that's why I was asking, because okay, when this concentration compactness doesn't work, there are also these kind of parabolic methods like harmonic net flow.
I mean, at least as far as minimization is concerned, it would seem reasonable.
I'm sorry.
Yeah, it would seem reasonable if you think of, by analogy with harmonic maps, that if you're in other homotopy class, then
Etienne, I don't hear you. Maybe is it just me?
do you hear me now?
I can hear you.
Okay, so I was saying maybe if you think of harmonic maps, it would seem reasonable that if you minimize in another class, then you would not have a minimum, right? It would degenerate.
I'm sorry, Etienne, but I don't hear you. I think your micro is closed.
I think so. Etienne, what you're saying is that if you don't constrain in any way, then other than the overall degree, then there's no reason to have a minimizer in higher degree.
Yeah, that's.
Yeah, I think that sounds right. Yeah. If you don't impose some symmetry.
Okay.
But I'm not sure about this n equals -1 versus n equals 1 question, because then there's not necessarily a splitting, which can happen.
Yeah, but you could imagine that the chiral term helps you when you have degree 1 because
That's right.
It makes the energy level lower.
Yeah, exactly.
And if you would be in the other class, then it would not. And so then the minimal energy would be this 4 pi, and it.
I think that's probably true. Yes.
Okay, so are there more questions or comments? So let's thank Stephen again. Thank you, Stephen.
Thank you.
So it was a long day, but it was a beautiful day with so many beautiful talks. Thanks to the speakers, and see you tomorrow. Wafa will share the sessions tomorrow. I will log in 15 minutes earlier if you would like to join and chat a bit. Bye-bye. Bye.
Bye. See you tomorrow.